So the first thing we need to talk about here is electron configuration, or more simply, how electrons are arranged in a given atom. Now, let's say some atom has 40 electrons. The atom is actually a meticulous organizer, and it's not just going to let those 40 electrons go and act all willy-nilly all over the place. They are actually amazing at organizing. So this is kind of like, in a very exciting analogy, when someone files papers. Because someone that's really organized with filing papers does a few specific things. And the thing is, they have different storage cabinets for each of a given category of papers. But then not just that, inside each of those cabinets, they have folders that are dedicated to different subjects, different topics, whatever have you. So just like how you can categorize a piece of paper and then subcategorize it into a given folder, electrons in an atom do the same thing. I first categorize them into a shell. I then subcategorize all the electrons in that shell into subshells. And then each of those subshells in that shell are then going to be subcategorized into orbitals. But we're going to go into each one of those individually in this kind of starting example. So to start it off, we need to talk about the shells. And the shells are what we usually see in the Bohr model as these rings. And if this is the nucleus, we start counting from the innermost shell to the outermost shell. And we denote that with the letter N for each shell, and then the number of shells, or the number of shell that it is. So this first one would be N equals 1. Then we have N equals 2 for the second shell, and then N equals 3 for the outermost shell. And if I had a fourth, fifth shell, they would then get, the consecutive numbers. Now, each one of these shells can only hold a certain amount of electrons, and each one of those is a rigid number. So if I'm talking about the first shell, and that's what I'm going to be talking about with these three lines, I'm just going to represent each one of those shells as a line here. This first shell would only get 2 electrons, hideous 2. The second shell would get the third electron, and then the next 7 for a total of 8. And then after those first 10 electrons are there, the next 18 will go into the third shell. Now, I'm going to try to give a way to familiarize yourself with this a little bit more, and it's the fact that these shells actually correspond to the rows on the periodic table. So I just have a small periodic table here, and all I'm going to do is each shell is just a row. So the first shell is the first row of the periodic table. So if I write down N equals 1, N equals 2, and let's say N equals 3, it's kind of going to be easy to start to see why this amount of electrons goes into each one of these given shells. So for the first row, there are 2 elements. And even though there are 2 elements, both of these elements have 1 more electron than the last. And so for each one of them, let's say for the first row, there are 2 total electrons. After those 2 electrons, I move on to the second row. And that second row, for N equals 2, has 8 elements. Each one of those elements has 1 more electron than the last, for a total of 8 electrons in that second row. The third row gets kind of silly, I guess, because instead of moving all the way to the end here and saying, oh, I also have 8, each one gets consecutively bigger. And for the third row, I don't just count this part and then the part on the far right. I actually move from here downwards taking out those 10 transition metals, and then follow through for a total of 18. So in total, I have 2, 8, 18. And now you shouldn't memorize, oh, hey, on the periodic table, I need to find out and memorize every single amount of electrons. Just because there's actually a formula you can use to find out how many electrons are in each shell. And that formula that I would recommend memorizing is just 2n squared, where n is the shell, and whatever kind of answer you get from this equation will be the total number of electrons that can be in that shell. And so if we're talking about, let's say, the fourth shell, that would just be 2 times, when n is 4, squared, and that would mean I have 32. So in the fourth shell of an atom, it can hold a maximum of 32 electrons. Now, let's say I know these electrons are getting put into these shells, but now those shells are going to be subcategorized. And so the way that we subcategorize those shells are with the next step, which is subshells. So now, let's say, in this n equals 1 shell, it represents and is broken down into only one subshell. Let's move this out of the way. In n equals 2, it's going to represent 2 subshells. And when n is equal to 3, it's going to represent 3 subshells. So the electrons in the third shell will be split up and divided among 3 subshells. Now, what are the names for these subshells? Well, the first subshell, and we'll use a different color here, is called the S subshell. For n equals 2, the first one is still going to be called an S subshell, but instead of being the 1s subshell for the first row, this is now the 2s subshell. And then we also have a new contender here, which is the P subshell. And then, following the pattern that's been laid before us, for the third series of subshells, we have the 3s, the 3p, and the 3d. And guess what? Just like before, this is representative of the representative. This is going to be represented on the periodic table. So on the periodic table, we can break up and actually visualize all of the different subshells. So let's say, what color did we use? We used purple for the actual subshells, so I'll keep that going. So for the first row, where n equals 1, I've got 2 electrons, or 2 elements. And both of those elements are actually going to be in the S block. And the S block overall is represented here and here. Now, what happens when we move down to n equals 2? Let me just write, whoa. This is S. Cool. So we move into the n equals 2 shell. We can see here we break into 2 subshells. And those subshells are the 2s right here, and then also the 2p. And all of these elements here are in the 2p block. Or sorry, they're in the p block. Only these ones are actually in the 2p block. So I will represent those. Why not? Let's just follow the flow with a p. Now, lastly, there is no d block in the n equals 2. But when we move down into n equals 3, we will get that D block. And that D block is going to appear right here. So just like you saw earlier with how in shells we move downwards right here, we do the same thing here. So this will be my D block. And we don't have it pictured, but down here would be my F block. But we're not going to worry too much about that right now. So here's all of these subshells, and it kind of makes sense. Now, we're still not done, because those subshells can then be broken down and subcategorized again into orbitals. So for all of the orbitals, let's just choose green. I'm going to have a number that depends on the subshells and the rows. Now, let's write down some information. So this is n equals 1, and also this is an S block. Both of these are n equals 2. This is an S block, and this is a P. And then for these three, this represents the third shell, and I have the S, P, and D subshells. Now, how many orbitals go into each one of those subshells? Well, just like before, this can be represented on the periodic table. Sorry I didn't give you guys this. So now what happens? So orbitals, and this is just something important to memorize, how many electrons go into each orbital? So what's the answer? It's 2. There are going to be 2 electrons. That's not proper grammar. Per orbital. Now, from what that means, it's going to be pretty easy to find out how many orbitals there are, because in n equals 1, I'm just going to use a consistent color for this. For n equals 1, I have 2 atoms. Each one has 1 electron more than the last, which means there are 2 electrons total. And if I have 2 electrons per orbital, that means I only have 1 orbital. And so I'll just draw a sideways circle to represent 1 orbital. Now, moving into the second one. Here is my 2s block, and there are 2 elements in that 2s block. And because there are 2 elements, and there's 2 electrons in those, or 2 subsequent electrons in those 2 elements, I'm going to have 2 electrons, 1 orbital. So the s will have 1 orbital. Here in the 2p block, I have got 6 elements, 6 subsequent electrons, or 3 orbitals. Lastly, in the D block, all of this stuff, or in the third row, the third shell, sorry, I have my S, which has 2 electrons. I have my P, which has 6 electrons across 3 orbitals. And then I have my D block. There are 10 elements there. 10 elements, 2 electrons per orbital means I have 5 total. So I hope that was helpful. The only thing we're going to do now, just to kind of summarize all of this, is write down that information in a table for the numbers of electrons in each shell, subshell, and orbital. So we'll just do that in a solid black. So for this first one, shell number, and then number of electrons, n equals 1, n equals 2, n equals 3, and n equals 4. And like we saw with the formula, that's nicely placed right there if you wanted to calculate it through that way. But just doing it fast, I have 2 electrons in the first shell, 8 in the second shell, 18 in the third shell, and then 32 in the fourth shell. Now, when we talk about subshells, let's talk about, again, how many subshells are in each shell. So shell number, 1, 2, 3, 4, and then subshells. There is the S subshell in the first shell. There are both the S and the P subshells in the second shell. There are the S, P, and D subshells in the third shell. And in the fourth shell, I have S, P, D, and F. Last but not least, orbitals. So, for this table, we'll just use the subshell, because each subshell, no matter whether it's an S, P, D, or F, each one has the same number of electrons, maximum. That is the S subshell, P subshell, D subshell, and then F subshell. The number of orbitals will be 1, 3, 5, and then if you look at the F block, there are 14 elements. 14 divided by 2 is 7. So that's the introductory lesson to electron configuration.